Okay, so chapter 7 continues probability, but now we're going to get more into probability that has more of like an actual formula versus just kind of reading it like we did in chapter 6. So we've talked about these before, but a random variable is a numerical variable whose value depends on the outcome of a chance experiment. So let's consider chance experiments where we flip a coin twice. It is possible the outcomes are heads, tails, tails, heads, tails, tails, heads, heads. In this experiment, a random variable could be x, the number of heads. What are the possible values for this random variable? Well, x could equal 0, right? Could have 0 heads, 1, or 2. Suppose we're doing a survey on hair color. What random variables could we consider? So if x was hair color, the problem is your answers aren't going to be numbers, right? You could have blonde hair, you could have black hair, you could have purple hair. Each answer is going to be a different category. So the values of a random variable have to be numerical. Thus, hair color cannot be a random variable. So a random variable, this is a throwback to chapter 1, the very first day of notes in this class. A random variable is discrete if its set of possible values is a collection of isolated points on the number line. So again, think people, right? You could count. There's not like half a person. Items purchased. Number of goals in a hockey game. Something you can basically count, right? A random variable is considered continuous if its set of possible values includes an entire interval on the number line. So think things you can measure. So temperature, weight, time is continuous even though we usually stop at a certain second. But technically it's continuous. Discrete random variables almost always occur when we are counting, and continuous random variables always occur when we are measuring. So if you kind of remember those two simple rules, you're pretty much okay. So hair length would then be continuous, because we're going to measure, but the cost of your last haircut is discrete. Okay, money is always discrete because you can only round to the nearest cent. So, is this an example of a discrete or continuous random variable? 3 coins are tossed by a student. X is the number of tails showing. That would be discrete because we would count again. 2 friends flip a coin until one gets 3 tails in a row. Let X be the number of trials required to win the game. Again, that's going to be discrete. You won't have half a coin flip. A person begins driving from home to Salem and will stop at a stoplight at some point on the trip. Let X be the distance from home when they're stopped at the light. That would be continuous. Right, because we're going to measure that distance. Okay, so going back to chapter 6, we did talk about this a little bit in chapter 6, but really this first section in chapter 7 is really going to get into probability distributions. So probability distribution of a discrete random variable x gives the probabilities for each value of x. This is usually done in a table, probability histogram, or a formula. We're going to deal with discrete variables today for the rest of the day. Tomorrow we'll get into continuous because it's a little bit different. So let x be the number of heads, 2 flips of a coin. I'm going to switch this and make this 3. Just so you can see it's a little bit, we're going to do 2 something in a minute. So the probability distribution of x would be, so again, you can have heads, heads, heads. You could have heads, tails, heads. Heads, heads, tails, tails, heads, heads. Now let's do two tails and heads. So tails, tails, head, tails, head, tails, heads, tails, tails, and then you could have all tails. So my probability distribution, the top's going to be x, the bottom is the probability of x. So x could either be 0, I could have 0 heads, 1, 2, or 3. Okay, so there's 8 possibilities. So the probability I had 0 heads, that would be if I got tails, tails, tails. So that'd be 1/8. 1 head would be down here, 1, 2, 3, so 3/8. 2 heads would be 3/8, and then 3 heads would be 1/8. So there's your probability distribution. So there are two things that we need to think about with the probability distribution. Sorry, I'm yawning. So for every possible x value, the probability has to be between 0 and 1. So x, you can't have any negative probabilities. They don't happen. So for every possible x value, the probability must be between 0 and 1. And then the sum of all the x values, so the probability of x has to add up to 1. So that's like the mathematical. Here, let me write it out in words. The sum of all the probabilities should equal 1. Now again, you can, especially when you get like with more decimals, you can get 0.99 or 1.01. Obviously, if there's a little bit of a rounding issue, but they should equal 1. It should never really go over 1 unless you're rounding. Okay, so x is the number of shots I make in 3 attempts. So what's the probability that I make all 3 shots? Again, if you know, we know all these have to add up to 1. I'm going to do 1 minus 0.1 plus 0.25 plus 0.5. So I'm going to add up all the other ones, do 1 minus that, so I get 0.15. So there's my missing piece. Hopefully you guys can see this. I make less than half my shots, so that's the probability x is, half would be 1.5, so less than or equal to 1. So that's the probability I make 0 plus the probability I make 1. So 0.1 plus 0.25, so 0.35. And I know I'm showing a lot of work, but this is showing work. So even if it's as simple as writing out the probability, notation, that's showing work in this section. I make at least 1 shot. So this is the probability x is greater than or equal to 1. So there's really 2 ways to do this. You can add up the top 3, 0.25 plus 0.5 plus 0.15, or we can do 1 minus the probability I make none of my shots. So it's not so bad with a table, right? You can easily add up, but if it's like gets more complicated, sometimes, like I said before in chapter 6, the 1 minus the none thing is a lot easier to do. Okay, let's try a story problem. It's known that 80% of all tomato plants sold at a local garden store bear tomatoes within 45 days. You have just purchased 2 tomato plants from the store and are interested in the random variable x equals the number of the 2 tomato plants which produce tomatoes within 45 days. Construct the probability distribution for x, assuming the growth patterns of the 2 purchased plants are independent. This is going to be key. We're going to remember stuff from chapter 6. The fact that they're independent means I can multiply the probabilities. So before we do our probability distribution, let's think about the outcomes. So I got 2 plants. I could have tomatoes in both. I could have no tomato in the first plant, tomato in the second. Tomato in the first, no tomatoes in the second. Or no tomatoes in both. Now the thing is, these are not just equal probabilities like we did with flipping the coin, because it's an 80% chance that you get tomatoes. So with the flipping of the coin, because it was 50-50, I didn't have to multiply any probabilities. Here I'm going to have to. So tomato, tomato would be like 0.8 times 0.8, so 0.64. Tomato, no tomato would be 0.2, 0.8, so 0.16. Here it'd be 0.8 times 0.2, so another 0.16. And no tomatoes in both would be 0.2 times 0.2, so 0.04. Okay, so now when I go to make my probability distribution, I have x, the probability of x. Again, I can have 0 tomatoes, 1 tomato, 2 tomatoes. So 0.04 goes in. 1, you got to put both of these together. So it's actually 0.32 because there's 2 ways for it to happen. And then 2 tomatoes was 0.64. So there's my probability distribution. Okay, let's try a little bit more complicated one. So we tried something with 2 things. We tried something with 3 on the front page. Now we're going to try something where there's 4. So in some areas in California are particularly earthquake prone. Suppose that in each such area, 20% of all the homeowners are insured against earthquake damage. 4 homeowners are selected at random. Let X be the number denote the number among the 4 who have earthquake insurance. Okay, so I'm going to put my probability distribution over here because I'm going to do some work here. So X, P of X. So I can have 0 people who have earthquake insurance. I can have 1, 2, 3, or 4. Okay. So this one is a little bit tricky. We're going to get more in depth on 1, 2, 3 kind of as we go throughout this chapter. So I'm going to do this strategically. I'm going to start with the outside because it's easiest to find 0 people having earthquake insurance and 4 people. So I'm going to do it off to the side. So the probability X is 0. None of the people have earthquake insurance. So if 20% do, that means 80% don't. So that's going to be 0.8 to the 4th power because it's 0.8, 0.8, 0.8, 0.8. Right? 0.8, 0.8, 0.8, 0.8. None of them have it. So that's 0.4096. So I'm going to add that to my table. Now, the probability all 4 have earthquake insurance is going to be 0.2 to the 4th because every single person does. So 0.2, 0.2, 0.2, 0.2. So that's 0.0016. So those are very much the easiest to do. Now, I'm going to go with the probability 1 person has insurance. So if you think about it, I'm going to give myself a little space here. 1 person does, that's 0.2. But then 3 people don't. So that's 0.8, 0.8, 0.8. Now, the thing is, this can happen 4 ways. The first person could have the insurance, the second, the third, or the 4th. So you have to take your answer and multiply it by 4 because there's 4 ways that can happen. So that ends up being the same as P equals 0. That doesn't happen very often. It just happens to happen here. So 0.4096. You're not always going to get these 2 are the same. Now I'm going to skip 2. The probability that 3 of them have insurance. Again, I'm going to leave a little space. That's 0.2, 0.2, 0.2, 0.8. So one of them doesn't. But again, that can happen 4 ways because the first person could not have it, the second, the third, or the 4th. So we're going to multiply that answer by 4 again. So that's 0.0256. Now, I strategically left 2 alone because instead of trying to figure it out, because 2 people having insurance would be 0.2, 0.2, 0.8, 0.8, but then you have to figure out how many different combinations that could be. We'll get to that later in the chapter when we get to 7.4 and 7.5. But for today, when you're doing probability, keep the middle for the end. I'm going to do 1 minus everything else. Because I know that this whole table's got to add to 1. So if I strategically put the hardest one last, I can easily plug that one in. So when I do 1 minus everything else, I get 0.1536. So then there's my table. Again, we'll get to this later in the chapter, but for today, just start thinking, okay, go from the outside in. So what's the most likely value of X? There's actually two answers. 0 or 1 homeowners having insurance. What's the probability at least 2 of the 4 selected homeowners have earthquake insurance? So again, the probability that X is greater than or equal to 2, at least 2. So I'm going to do 0.1536, that's 2. 0.0256, that's 3. 0.0016, that's 4. So I get 0.1808. Okay? So that's really probability distributions for a discrete variable. Like I said, tomorrow we'll look at continuous, and then we'll get more in depth with how do you find this stuff in 7475.